So welcome back to our conversation about permutations and combinations. In part 1 of our video, we spent a good bit of time talking about a permutation. And in a permutation, we use notation like, a big P. And say we have 7 things to choose from, and we're choosing 3. And the formula for that was 7 factorial over 7 minus 3 factorial. We even talked about how to substitute that in our calculator, and we did some examples of word problems that required a permutation. And again, what's important about a permutation, just to review, is order of your outcomes matters, and you're not reusing whatever it is you're building your values with. Okay, now I want you to focus on question number 3 that I actually presented in the first part 1 video. And how many ways can the club select a 3-person committee? Now, notice our club has 5 members. And we're selecting a 3-person committee, right? So if we go back the old way of handling this, with a 3-person committee, we have 3 tasks. We're selecting the first person, the second person, and the third person. Now, if we have 5 people to choose from, we have 5 ways to select the first person, right? We can't reuse people because that would mean we don't have a committee of 3 people. If we reuse somebody, that's just 1 person. So after we pick somebody, we got to throw them out of the list, and then we have 4 people to choose from, and then 3 people to choose from. Okay, and then that would give us, on a quick calculation, 60 options. But then we realize, because we're just creating a committee and not a list of officers, if one of our lists, or one of our outcomes was, let's just say Barbara, I'm going to use B for Barbara, C for Catherine, and E for Erica. Well, also in that list would be Catherine and Barbara and Erica, right? Also in that list would be Erica, Barbara, and Catherine. And it starts to make you wonder, how many of these repeats would we have? Well, then it turns into a subset situation. Well, it turns out there's 6 of them. Should we list them all? Let's do that in an organized fashion so you could just see. So we have Barbara, Catherine, and Erica. Okay. How about, so we did B, C, E, and then let's do B, E, C is an option. Now, I can't think of any other way that Barbara could lead the crowd, right? We did every option there. So now let's let Catherine lead the crowd. So how about C, B, E, and then C, E, B. And then also Erica could lead the crowd. And then that would be E, B, C, and E, C, B. Now, are there any other ways we could rearrange the letters B, C, and E, which represent Barbara, Catherine, and Erica? Can you think of any other ways we could arrange that? I cannot. It looks like 6 of them. But those are repeats. And whenever you have repeats, remember, we're supposed to divide those out. Now, really what's going on here is in terms of permutation. This is a permutation of, that's supposed to be a P, not a weird looking B, a permutation of 3 choose 3, and that does equal 6. So what we need to do is get rid of those 6, and turns out that calculation, y'all, is just 3 factorial. Okay, so that gets a little bit complicated, but what it comes down to is order matters. Now, what we did here was a permutation. Now, that permutation, right, that's what we used in the calculation, was 5 choose 3. But then we divided it by a permutation of 3 choose 3, because we had repeats. Right? So I wonder if we can make a formula that would be a lot easier to think about than what we're doing right here. And we do have a formula for that. And so if you'll notice in green here, we have a formula for what we call combinations. Now, if we read what it says the number of combinations or subsets of n distinct things taken r at a time when r is less than or equal to n can be calculated as follows. So notice the notation for a combination is a big C. It's got a number, a subscript number in the front of that. That's how many things you have to choose from. The number after that in subscript, the R value, is how many things you are choosing. Notice the formula is your permutation that we've already worked with divided by the repeats. You remember, if you have a president and a vice president and a secretary, order matters. But if you have those same three people just making a subcommittee, you've got to divide out all the different permutations of those three people. So that's what that is, dividing out the repeats. And that gives us this formula right here. Now there's two things that are terribly important when you're using this formula. You only use it when you have no reuse of your values. So no reuse. And you also use it when order does not matter. Just like when you're building a subcommittee or a committee of people from a group of people. It doesn't matter if it's Bill, Charles, and then Evelyn, or Evelyn, Bill, and Charles. It's the same exact group of people. All right, so got a problem here for you that doesn't necessarily use this formula right off the bat. The way it asks the question, it just says how many subsets of the set A, B, C, D that contain three elements are there, and they want us to list the subsets first before we find out how many elements there are. There are different ways to list subsets. You could do the branching thing. Let me talk to you about that. You could branch and go, A, B, C, D. I'm just going to start this process. I'm not going to finish it. And then say we pick A first, then we could pick B, C, D, right? If you pick B first, you could pick A, C, D. C first. You see where I'm going with this? And then we'd have to branch again to get the third one. Now, the problem with this method is that it gives you the repeats, right? Which is the same thing about permutations. You get all the repeats. Notice this pattern already. If I pick A first and then B, that's going to be the same possible list if I pick B first and then A, right? Now, what you branch off after that, you would go down that path, but those are the same subset. So instead of listing them like this, because whenever you do this branching thing, order matters. And so let's just list them. So if I were to list the subsets, let's don't worry about the curly brackets. Let's just say A, B, and C is definitely a subset of, there we go, the set A, B, C, D. What's another one? What about if we do A, B, and D? And that's every way we could have A and B, right? If A and B are together, then C one time, D another time. Now let's throw out all the A and B together, and now let's work with A and C together. So if A and C is together, then you could have, you've already got A, B, C, so we're not doing that. You could have A, C, D, and then we're done with that list. And now, how about B, C, D? Now again, we're not doing C, B, A. You're not rearranging these. Is there any other way that we could list a subset, okay, with only 3 of these letters? Not every subset, just only 3 of the letters. I don't see any other way. I've gone through, and that's what the silence was, me checking again. It looks like there are only 4 subsets. But the point I'm trying to make here is that if you do it this way, that's fine. But you're going to have to throw out all the repeats. Now, if you do it this way, you get a bunch of them, because that's a permutation of 4 to choose from, and you're choosing 3. But when you list subsets, you're trying to get rid of the repeats. In other words, the order does not matter. And so that's the same as finding a combination. How many do we have to choose from? 4, because we have A, B, C, and D. That's 4 letters, and we're choosing 3. Now let's play around with the formula. How about we do that? So here's the formula above. The first number listed in subscript, just like with permutations, that's the n value. So I have 4 factorial divided by r. So this is what's new compared to a permutation, and that's dividing out all of the repetition. Like CBA, it would get rid of that one. So we're dividing by r factorial, which would be 3 factorial for this problem, times the part that's in a permutation already, 4 minus 3 factorial. Okay, and then write down what you have. You have 4 factorial over 3 factorial. 4 minus 3 is 1 factorial. Y'all, 1 factorial is just 1. So that's 4 factorial over 3 factorial, because that's just 1. So that's times 1 if you want to write it. Now, 4 factorial, you write it down as 4 times 3 factorial over 3 factorial, and the 3 factorials cancel, and that gives you 4. So look, that is all we have here. We didn't leave any of them out. That is all the subsets. It's 4. Now, the way I originally did this problem in the video is I did this branching over here, and I tried to find all the repeats, but it just turned into a big, huge mess. And so I decided to talk, rather than writing it as order matters and then divide out by the repeats, which would have been effective, it's just huge, I decided just to list all the subsets like we did way back in the sets section. And you see there's 4 of them, and if you use the formula, there's 4 of them as well. So let's practice using that formula. And we have problems here. The first one, I have a combination of 7, choose 3. So if you use the formula, remember the first number listed to the left is your n. The second number listed on the right is your 3. The C means you're doing a combination, not a permutation. And again, a combination means the order that your values are in does not matter. So when I write this formula out, it's 7 factorial divided by the second number listed, 3 factorial, also divided by them subtracted from each other, 7 minus 3 factorial. Now to simplify, I'm going to say that's 7 factorial divided by 3 factorial times 7 minus 3 is 4 factorial. Now hint here, write the top one down to the biggest one in the denominator. Since 4 is bigger than 3 factorial, I'm going to write 7 times 6 times 5 times 4 factorial divided by 3 factorial times 4 factorial, and what's going to happen is these 4 factorials are going to cancel each other out. Continuing on, this is 7 times 6 times 5 divided by, we know 3 factorial is 3 times 2 times 1. Now, I do see something here that you might not notice, but this 6 cancels with the 3 times 2, because both of those are 6, and then I can just do 7 times 5 is 35 divided by 1, which is 35. Didn't even need my calculator at all for that one. Now, often I do, okay, that was just one situation where I could do all that just in my head, and that's always nice to me. Now, continuing on with the next one, again, the first number listed, bottom left, always goes on the top with a factorial. The second number listed when you're dealing with a combination goes straight in the bottom, but don't forget to subtract the 2 and then put the factorial on the outside. Then you need to do your subtraction. So I have 11 factorial divided by 5 factorial. We know 11 subtract 5 is 6, and the factorial goes with that. Now what am I going to do? I'm going to write the top one all the way down to the biggest factorial that's in the bottom. Sometimes it might be the first one listed. In this case, it's the second one listed, just like the last time. So I'm going to say 11 times 10 times 9 times 8 times 7 times 6 factorial divided by 5 factorial times 6 factorial. Okay, what am I going to do now? I'm going to cancel the 2 6 factorials. They, boom, cancel each other out. Then I continue to simplify. So that's 11 times 10 times 9 times 8 times 7 divided by 5 times 4 times 3 times 2 times 1. Now, if you want to cancel some of that, you can. If you just want to type that in your calculator, you go right ahead. If you want to find the combination button in your calculator, I don't have a little segment like I did in the last video to show you how to do this in your calculator, but if you figured out permutations, I guarantee you combinations is right next to it. So, but I do see that this 10 cancels with this 5 times 2. If I want to do that. I also see that 3 divides into 9, but that might be more than I want to fool with. And so I'm just going to type in my calculator 11 times 9 times 8 times 7 divided by 4 times 3 times 1. Now on the bottom I know that's 12. So I could say 11 times 9 times 8 times 7 divided by 12 and see what I get. And I get 462 possibilities if I have 11 things to choose from and I'm only picking 5 of them at a time, and then the order the sets are in does not matter. Okay, and then finally 6, 2, 6, let's try that out. Okay, so if I have, that'd be 6 factorial, right, divided by 6 factorial times 6 minus 6 factorial. That's the way the formula works. So this one goes on top, this one goes second, and then we subtract the 2 that go here. Well, this is 0 factorial. So now I have 6 factorial divided by 6 factorial times 0 factorial. Look, this 6 factorial cancels with that one, right? And when you cancel, that leaves you with a 1. And 0 factorial is also 1, which gives me 1. Does that make any sense? Well, look, y'all, if you have 6 things to choose from, and you choose all 6 of them, and the order that they're in doesn't matter, there's only one way to do it. Just grab them all, right? And that's it. Okay. It's just like if you're trying to build a team for kickball, right? And you only have 6 people to choose from, and you just pick all 6 of them. There's your one team right there. There's no other options for your team. And here's a page you might think comes in handy. A problem-solving strategy for each of these. Notice it says for permutations. So permutations can be used anytime we need to know the number of arrangements of R objects that can be selected from a collection of N objects. The word arrangements implies an ordering. So you ever see the word arrangement, I want you to think permutation. 2 things are important about every permutation. Repetitions are not allowed, so no reuse. And order is important, so think about president, vice president, secretary. On the other hand, for what we just did, a combination, okay, order is not important, all right? Repetitions are not allowed. That's common to both of these. Repetition is not allowed. If you have a problem that uses repetition, then you can't use a permutation or a combination. You have to go back to just the basic multiplication principle. But the thing about a combination is order is not important. You're just talking about a group of people, okay, or a group of things you just throw in a bucket. The order they land in the bucket is not of issue at all. Now, something that may or may not help you, but I want to write this down because I think it's funny. A combination lock. Y'all have had them, right, on your locker at school. A combination lock is not a combination. Why not? It's a permutation, but why not? Well, you know, if your combination lock is 36, 18, 45, the order matters, right? You're not allowed to type in 18, then 36, then 45. It's not a combination at all. It's a permutation. So to help you memorize this, maybe you should do this. A combination lock is not a combination. So you know that for a combination, order does not matter. So for example, G, we have a common form of poker involves hands. Now, if you're not familiar with cards, I've got a little problem coming up with that explains cards. But in this particular problem, you don't have to understand a deck of cards because it tells you have 52 cards. In a common hand of poker, you select 5 cards. Okay, each dealt from a standard deck of 52 cards. How many different 5-card hands are possible? So you don't need to know what a deck of cards looks like. You just know there's 52 cards and somebody's going to hand you 5 of them. But the question is, how many different ways can somebody hand you these 5 cards? In other words, what kind of combinations can you get? Now, when you're handed those 5 cards, you can order them however you want to, which means order does not matter. You can put them in your hand however you want it. You can pick them up from the table just as they are, or you can move them around. It's the same hand of cards. So really, y'all, this is just a problem that's a combination because order does not matter. You're not reusing the cards because once you throw one out to somebody, you can't put it back in the deck. So you're not reusing the cards. And there's 52 to choose from, and you're just picking 5 of them. So let's do that calculation. So remember, the first number is what goes on top. That's 52 factorial. The second number goes on the bottom, only when you're dealing with a combination. And then you subtract the 2. And subtracting the 2 is in both formulas. Okay, so that gives me 52 factorial divided by 5 factorial times 52 subtract 5 gives me 47 factorial. Now remember, the rule is to simplify, unless you're going to plug this combination directly in your calculator, then you need to write the top one down to the biggest one in the bottom. So I'm going to write 52 as 52 times 51 times 50 times 49 times 48 times 47 factorial. I'm not going to write it all the way down to 1, first of all, because that's a big pain. Second of all, I got an easier way to handle it, right? Now, 5 factorial, I'm leaving alone, and here's 47 factorial also. Now, the reason I did that is so I could cancel this 47 factorial with this 47 factorial. That's the only reason I wrote the top one down to the biggest one on the bottom. Then you keep going with your calculations. That's 52 times 51 times 50 times 49 times 48. The 7 factorial is gone, divided by 5 times 4 times 3 times 2 times 1. And if you wanted to simplify at this stage, you could, or you could go directly to your calculator, and I'm just going to type that in. So 52, I'm going to be real careful, times 51 times 50 times 49 times 48, no 47, right, divided by 5. Now I need to put that in parentheses. That's going to be 5 times 4 times 3 times 2 times 1. And that gives me a big number, 259. And then it says 8960. Now when I read that, that's 2,598,960. And that's how many possible poker hands there are in a single deck of cards. Okay, so example H is a problem directly out of the homework from the textbook. It says Sonia Johnson wants to name her baby so that his monogram, first, middle, and last initials, will be distinct letters in alphabetical order. And he will share her last name. How many different monograms could she select? So let's think about what this is saying. Often that's what you have to do, is break down the problem. Now, we have a place for your first, middle, and last, right? First, maybe let's call that F instead. So first, middle, last. Now his last has to be the J for Johnson. So really, all you're selecting is the first initial and the middle initial. Okay? Now, order does matter because it's in alphabetical order, right? So first, middle, last. That gives you the wrong impression that order matters for this problem. It really doesn't, because you're just selecting 2 letters and you're going to put them in alphabetical order. You see what I mean? So an example here, like A-B. Like she could name her kid Abbott Brantley Johnson. I'm making up something crazy, but you see what I mean? Or you could have C, anything before J, so F, okay? Charles, what begins with a F, Fitz Johnson. All right, so that's what's happening. The order the C and the F in actually come in don't matter. Why? Because if it came in as FC, that's not going to work. We would just flip it around to CF because Sonia wants her baby's initials in order. So we know we're selecting 2 letters. So when we build our combination formula, we're choosing 2. Now, how many can we choose from? This is where it gets interesting. We can't choose 26, right? Because since Johnson comes last, then our letters have to be before Johnson. Also, distinct letters, that's another thing. We're not reusing. Remember, to use a combination or a permutation formula, you can't reuse anything. And so to use the formulas, it has to be distinct. Whatever we're saying needs to be distinct. So we could choose from A, B, C, D, E, F, G, H, I. Why not J? Because we already used it, right? J is already included here for sure, and it says distinct letters, so we can't use J again. Now, how many letters is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9. So this problem is 9 combination 2. Again, it's tricky. This is why I picked it. Because when you think alphabetical order, the first thought is it's a permutation because order matters. But order matters in what she's doing, not in how we're picking the numbers. I mean, the letters. We just picked 2 letters, and Sonia puts them in order for us, okay? If we did it as a permutation, we'd have too many examples. Like one of our outcomes. One of our outcomes would be BAJ, and that's not allowed because Sonia wants it in alphabetical order. So let's do this calculation. So we have a combination of 9 choose 2. Remember, the first number goes on the top, 9 factorial. The second number goes on the bottom when you're doing a combination. And then what goes in, no matter if it's a permutation or a combination, you subtract the 2. So you got 9 factorial over 2 factorial times 7 factorial. Our next step, if you don't use the combination button in your calculator, would be to write the top one down to the biggest one on the bottom. That's right there. So you do 9 times 8 times 7 factorial divided by 2 factorial times 7 factorial. And then what happens is the 7 factorials cancel. And that gives us 9 times 8 divided by 2 times 1. Hey, I could do this in my head, right? 2 goes into 8 4 times. That gives me 36 options. So Sonia has 36 different options for letters that she can choose to name her baby so that the baby's initials are in alphabetical order and it ends with a J. Now I have a page here for you that I got out of the book that I thought was pretty great. How do you decide when to use a permutation and combination? I'm going to go ahead and tell you, it's not always easy to kind of break through all of your word problem information to figure it out, just as the example for the last problem. But there are some hints here of which to use and in which situation. But notice, for either a permutation or a combination, one of the things that's common to both is the number of ways of selecting R items out of N items. So you're going to know how many items you have to choose from, and you know you're going to be selecting some of them. Now, the R and the N could be the same, like 6 choose 6. You know what I mean? We did a couple of problems like that. Also, repetitions are not allowed. If you have a problem that has repetition in it, like you're allowed to reuse a letter or reuse a number or reuse some other thing, then you can't use a permutation or a combination. You have to go back to the multiplication principle that we learned in section 10.2. Okay? For a permutation, order is important. For a combination, order is not important. Just like the initials that we did just a minute ago for Sonia's baby. I know it seems like order was important there, but it wasn't because she just needed 2 letters. She was going to put them in alphabetical order. We didn't have to do both situations like an A and a B and a B and an A. All right, now, arrangements of the N items taken R at a time. Keyword here for a permutation is arrangements. If you ever see arrangements in your problem, you know that you're dealing with a permutation, okay? On the other hand, combinations are just subsets. You're just trying to combine everything together. The order it's combined together in does not matter. So subsets of an N items taken are at a time. And so subsets is a key word for combinations, although you won't always see subsets, just like you won't always see the word arrangements either. Again, clue words for a permutation are arrangement, schedule, order. Okay, but again, we just did a problem a minute ago that said alphabetical order, but it was a combination. So you even have to be careful with that. For combinations, keywords are a set, a group, a sample, or a selection. And Sonia wanted to select, you know, maybe you could use that. Really, you just have to understand the problem to decide. And again, if you throw that extra thing in there I talked to you about, a combination lock is not a combination. Now, why am I asking you to think about it that way? Is because that'll remind you that for a combination, order does not matter. for a combination lock, order matters, right? So it actually makes a combination lock a permutation and not a combination. And maybe that'll confuse you. I hope not. I'm hoping it'll help you remember which one is which. Now, what I'm going to do is come back for a third part 3 video, because I have several more just problems to do where we determine what situation we have. And before I jump there, I'm going to show you one more hint to help you with some problems, and then we'll come right back to that page. So when you're doing problems, problem solving strategy, the particular conditions of a counting problem will determine which specific problem solving technique you can use. Number 1, if selected items can be repeated, you use the fundamental counting principle, which is not a permutation or a combination. It's neither one of those things. So they threw out an example here. How many 4-digit numbers are there? Okay, then you would just do, remember we did this problem. The 9 comes from, you can't include a 0, and then you pick the next spot and the next spot. So basically the multiplication principle is when you have your dashes. Okay, so pick the first number, the second number, the third number, the fourth number. So when you pick the 9, you had 9 different options. Well, you picked the first one, you had 9 different options for numbers because 0 is not included. But when you pick the second number, it could be a 0, so there's 10 possibilities. The third number could also be a 0, so there's 10 possibilities. And the fourth number could be a 0. So that's why they have this here. Now, that's because you're reusing your numbers. 1000 is a counting number. It fits into this problem. Now the second option here, or possibility for your problem, if the selected items cannot be repeated, okay, so you're not reusing, but order is important. How many ways can 3 of 8 people line up to a counter? Okay, or get a picture made, or be president, vice president, secretary. All of those situations, the order matters. And so you would do 8, choose 3. Third situation, items cannot be repeated. Notice that's the case for both of these, a permutation and a combination. You cannot reuse items or repeat items. And order is not important. So it says, how many ways can a committee of 3 people be selected from a group of 12? Anytime you're building a committee or making a subset, okay, then the order does not matter. So that's what this part is for. You subtract out the duplicates, and your number would always be smaller for a combination than it would be for a permutation of the same situation. Of course, these are 2 separate problems. So when you come back, I'm going to go through this page once again for part 3, and then we'll do several problems where we've just got to decide what of these 3 situations do we have.